Hello everyone. Thanks to everyone for watching this video. My name is Qida. I am an architect and engineer. Today's video is titled Plastic Bending, and it is going to provide you a broad overview of plastic hinges and also the analysis of plastic columns. I am going to give you an overview of what I am covering in today's video. First at all, we will have a look at some fundamentals of the plastic hinges, then move on to the plastic analysis of columns, then wrap up with conclusions. In a framed structure, the applied forces are resisted mainly by shear forces and bending moments in the members. Before considering the collapse of frames, it is necessary to examine what happens to a member when it bends enough to cause the most highly stressed material to yield. The simplest structure which resists load by bending is the simply supported beam, as shown in Figure A. It has an effective span L and carries a central vertical load W. The load is carried to the supports by the beam bending. When the plastic hinge forms in the simply supported beam, collapse occurs, as shown in Figure B. The plastic hinge is formed at a moment MP equal to the plastic moment of resistance of the section, which is the largest bending moment that the section can carry. A rectangular section is shown in this figure. The stress distribution due to the formation of a plastic hinge by bending about the y-axis is also shown. Since the hinge has been formed by bending only, horizontal equilibrium of section requires that C equal to T, where C is the compressive force equivalent to the yield stress acting over the area of the cross-section in compression above the axis of zero strain, and T is the tensile force equivalent to the yield stress acting over the area in tension below the axis of zero strain. In this case, the axis of zero strain is half of D from the top of the section, and C equal to T equal to B times D over 2 times sigma y, where sigma y is the yield stress. Since these forces are caused by a bending moment equal to MP, taking moments about the axis of zero strain gives this expression, and this is sometimes written MP equal to S times sigma y, where S is called the plastic modulus of the section. The plastic modulus is a geometric property of the cross-section. Now we know how to determine the plastic moment of resistance MP for a simple beam. Next, we will introduce a combination of bending moment and axial force. Columns may have to carry significant axial forces in addition to bending moments. The axial force P moves the axis of zero strain as in this figure. To simplify the mathematics, the stresses have been replaced by two equivalent distributions. The stresses in A are assumed to be wholly due to the axial force. That is P equal to B times Z times sigma y. The stresses in M are caused by the changed plastic moment MP dash, and is given by this equation. B times Z squared over 4 times sigma y is the plastic moment MP of the rectangular section, so that we have this expression. The maximum axial force PP, that is the section can carry, ignoring buckling, is called the squash load, and is given by PP equal to B times D times sigma y, so that we have this equation. This equation shows that both tensile and compressive forces reduce the plastic moment because the reduction term is P over PP squared, which is always positive. This equation is plotted in this figure. Next, we will introduce the combination of bending moment and shear force. Generally, beams must resist the combination of a bending moment and a shear force N. This means there is usually a combination of direct stresses sigma from the moment and shear stresses tau. In these circumstances, the shear and the direct stresses interact with each other in causing the material to yield. In order to determine the onset of yield, a yield criterion has to be used. The Triskaj and von Mises yield criteria are most commonly used for ductile materials, where there is a combination of shear and direct stresses. Both criteria require that equation for yield to occur, where tau y is the yield stress in pure shear. Consequently, the individual stresses, sigma and tau, cannot reach their full yield value unless the other is 0. In general, this means that it is impossible for the full plastic hinge stress distribution to develop. The shear stresses have to be 0 at the free edges at the top and bottom of the section, so the direct stress can reach its yield value there. Generally, this yield will spread in walls, leaving a core of material carrying shear and direct stresses. In a rectangular section, theory suggests a parabolic distribution of shear stress with maximum stress at the mid-depths. It would be reasonable to assume this still holds in the core and that the maximum stress in mid-depths is tau y when the plastic hinge forms. We should be able to show that the reduced plastic moment in this equation, from the direct stress distribution in this figure, and from the shear stresses that n equal to 4/3 times b times z times tau y. The full plastic moment mp and the maximum possible shear force np, assuming the yield shear stress over the whole section. Thus, we have this equation. Notice that z max is half of d. If that is substituted in n expression, it can be seen that the mp' over mp equation only holds if n over mp is less than 2/3. This is plotted in this figure. From these figures, it can be seen that in low-rise structures, axial forces are too small to have any significant effect on the plastic moments. In high-rise structures, they are more important and allowance must be made for them. From conclusions, what we learned? It has been concerned with yielding at a particular section of a member in bending. When full yielding has taken place and unrestrained plastic flow occurs, a plastic hinge has formed. The plastic hinge and plastic moment concepts are idealizations of the true section behavior. Axial and shear forces can affect the magnitude of the effective plastic moment, although they are not usually significant factors. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative, and that you learned some things from it. If you do have any questions, then you can write comments and messages. I'm happy to answer any questions. Thanks for your watching.